Okay, so today we'll finish these notes up. Shouldn't take too terribly long, I wouldn't think. All right, the first few slides have to do with uh, detecting and measuring earthquakes, measuring the strength of earthquakes. So the magnitude is the kind of the scale that we use now. We used to use something called the Richter scale, which was developed by the scientist Charles Richter in 1935. We don't use the Richter scale anymore. We use the magnitude, or we talk about the magnitude of an earthquake. Similar to the Richter scale, as the numbers get bigger, the earthquakes are bigger. They're more powerful, more destructive. Something to remember is that when we're talking about magnitude, as it changes from one number to another number, or one number to the next number is 10 times bigger than the previous number. So if there's an earthquake, if you're comparing an earthquake that's a 2.0 and a 3.0, the one that's a 3.0 is 10 times bigger than the 2.0. So it's not just a linear increase in the amount of power or the strength of an earthquake. Just like these circles, to kind of show the strength of an earthquake, this one circle is a 7.0, but then this big one is a 9.0, because a 9.0 is 100 times more powerful than a 7.0. Since going from a 7 to an 8, it's 10 times bigger. 8 to 9 is 10 times bigger, so 10 times 10 is 100. So the 9.0 is 100 times bigger than the 7.0. All right, so getting into detecting earthquakes, we detect earthquakes with a machine called a seismograph. So that's the machine. The seismograph is the machine that detects earthquakes. The paper that machine produces, or the data or the information, that's the seismogram. So if a scientist is interested in studying an earthquake, a scientist would use a seismograph to generate a seismogram. The seismogram is the information that a scientist would look at. Seismograph is just the machine that makes it. It detects the earthquakes and then creates this printout of data. And these are the things that I'm sure everyone has seen in the movies. The earthquake starts and the ground starts shaking, and there's a needle that starts going back and forth. And the larger the earthquake, the more the needle's moving, and all that. So, and there are several different styles of seismograph. That's kind of the most recognizable type that you're going to see. And let's get that one. All right, so here's an aerial photo of a portion of the San Andreas Fault, which is in Southern California. So remember that that's a sliding or transform fault, so it has two plates moving past each other. And this line right down the middle, that's the fault itself. So on either side of that are different plates that are moving past each other. It's just another picture of that, of the fault. And then this map shows in the continental United States, this shows areas where there are where there is a lot. So go back to that one. Okay, you're welcome. All right, so this map shows areas where there is seismic activity, where there's earthquake activity. And seismic is just another term that means earthquake or anything that's related to that. So the higher that peak is on this map, the more earthquake activity there is. So you can see down here in Southern California, the peak is really high because they have a lot of earthquakes there. There's a lot of seismic activity there that happens every day. Now, most of it is too small for humans to feel, but because we have pieces of equipment like seismographs, they can detect those earthquakes, those very small earthquakes, and record that information. An area that we'll talk a little bit about is this peak kind of in the Midwest, that's in the southeastern corner of Missouri. We'll talk about that here in just a minute, because that would affect us since we live in Indiana. That would definitely affect us a lot more than what's going on in California. Okay, so whenever there is an earthquake, the earthquake generates and creates different types of waves. It's not just one type of wave that's created when there's an earthquake. One type of wave, and kind of the first one, is a primary wave. So it's a P wave, which stands for primary. It's a compressional type wave, which means that it compresses the earth and then it expands. This is a similar wave to how sound travels. This is the fastest of all the waves that are generated from an earthquake. So it's the first one to get anywhere on Earth. So wherever the earthquake happens at the focus, and those waves move out, the P waves are going to be the first waves to reach something. Something important that we'll talk more about later this week, something important about P waves, and it can move through all phases. So it can move through solids and it can move through liquids. And it's not so much liquids like oceans or lakes or anything like that. It's more of the Earth's outer core that's liquid metal. P waves can move through the Earth's outer core. So that's something that's kind of unique about it. And like I said, we'll talk more about that later this week. The second type of wave, which we call S waves, that stands for secondary wave. This is a shearing wave. So this is a side-to-side movement. So as it's traveling in one direction, it's moving from side to side. These are slower. So this would be the second type of wave that would arrive. S waves do a lot more damage than the P waves. P waves typically don't do a lot of damage, but the S waves do. And something important to remember for later in the week is that S waves cannot move through liquids. P waves can move through liquids and solids. S waves cannot move through liquids. S waves can only move through solids. Like I said, we'll talk more about it later this week, but I at least wanted you to see this portion. And then the third type of wave, an L wave, or we refer to it more as a surface wave. These are the slowest. These are also the most destructive. And these are more up and down, like wave in water or something like that. It's more that up and down. So you have P waves, S waves, and surface waves. So those are the three types of waves that we're going to talk about here in class. All right, so this map, this just shows the eastern United States and epicenters of earthquakes. So you can see this little group of earthquakes down in the southeastern tip of Missouri. So here we have Kentucky and Tennessee, Arkansas, and up here is Indiana. So Indiana is really close. Where these earthquakes are, there's a town and a fault or a break in the crust called New Madrid, which has generated some very powerful earthquakes in the past. Here's just another map showing where it is, kind of in the middle of the plate, which is not the most common place to have a fault, but it does happen, obviously. This map shows 20 years worth of earthquakes from 1975 to 1995. And when you plot out where the epicenters are, you can see by the grouping of them, where the fault is. It's where they're, really tightly grouped together and overlapping. But it shows you or gives you a good picture of where that fault is, because that's where the earthquakes are happening. And again, from there, Indiana's in the upper left-hand corner or upper right-hand corner. And it's not very far, really. Just a few hundred miles away. And then this shows a few earthquakes that have actually started in Indiana. So the epicenter is actually in Indiana, which is not very common. We usually don't have earthquakes that start here, but it does happen from time to time. All right, and this just shows damage from earthquakes from different places around the world. And so here's some San Francisco, which is in Northern California, which they have a lot of earthquakes. Alaska had a really big earthquake in 1964. This is also Alaska. This is not Alaska. I don't know where this is, somewhere in Asia. I'm not sure where the Hotel De Carlo is, but it was broken. I'm not sure where this one is either, but a building fell over. This is an example of a phenomenon that we'll talk more about later this week called liquefaction. Basically what happens is while the earthquake is taking place and while it's shaking, the ground basically turns to a liquid because of water that's in the ground and water that's in the soil. And then when the shaking stops, it becomes solid again. So with this, when the earthquake was occurring, liquefaction happened, the ground became soft, and those buildings basically began to sink into the ground. And then when the shaking stopped, then that ground becomes solid again. So like I said, we'll talk more about that later this week. I'm not exactly sure where that is. We have a few pictures from Haiti from 2010. They had a very large earthquake, very deadly earthquake. This is the presidential palace. One of the reasons this was such a deadly earthquake is because of concrete. Because of the climate in Haiti, concrete is something that's really good to build with because Haiti is so hot, a lot of moisture. But concrete does not do well with earthquakes. It doesn't like to bend. It doesn't like to twist. It doesn't like to move. So a lot of times it doesn't. It'll just break. So that was one of the problems down there, aside from it being a really large earthquake. And then these last two, this is from an earthquake called the Loma Prieta earthquake. which was in San Francisco or around San Francisco. This is a bridge. And the second picture, you can see it a little better. The bridge had 2 levels. And it had these large, supporting legs. But a number of those failed. A number of those broke, which this is a better picture of, all this concrete, gave way and it broke. And that resulted in the top level of the bridge falling on the level below it, which, unfortunately, killed a number of people. As they were driving, it crushed them. But it is a good example of, how concrete does not do well with earthquakes. Okay.